So section 9.2 is just carrying on with the ideas we covered in section 9.1. It's really just kind of a bunch of practice and actually applying it in practice. But there's really not a new theory in here. So this is again, remember in chapter 8 how we did things about everything with a population proportion, and then we did the same thing with mu. Where we had a mean. Same thing here. We're going through and we're doing everything with population proportion first, and we'll come back and do it with sample means and whatnot later. All right. So the objectives for this section: make sure we know the same requirements that we had to do to find a confidence interval for a population proportion still apply when we're talking about um, when we're testing for significance. So just keep in mind, we'll review those, but those same three things we have to check, we still have to check in this section as well. And then we'll learn how to perform the significance test, we'll interpret the power of the test, and describe what factors affect the power of the test, and describe the relationship among the probability of a type 1 error and the probability of type 2 error in the power of a test. All right, so let's get started. So let's go back to the same example that we talked about before. We had a basketball player who claimed to be an 80% free throw shooter, and in a simple random sample of 50 free throws, he made 32. So his sample proportion of made shots was 0.64. Again, much lower than what he claimed. Um, so we analyzed it and we saw, well, it was highly unlikely in a simulation we ran. It was highly unlikely to happen. So we thought he probably was not telling the truth. But does it provide convincing evidence against his claim? So let's perform a significance test of our null hypothesis is, that the probability or the proportion of his successes is zero point 0.8, or the alternative hypothesis that his actual proportion of success was less than zero point 0.8. So, um, so those three conditions that we learned in chapter 8 still apply. So random, first off, the data has to come from a well-designed random sample or randomized experiment, right? If it doesn't come from a random random sample, then it's no good. The 10% rule, if we're sampling without replacement. So again, basically we can't. The population has to be at least 10 times what the sample size. In large counts, both n times p naught and n times 1 minus p naught are at least 10. All right, so check the conditions for performing the significance test on the virtual basketball player's claim. So again, first things first, random. It's just a bunch of shots. So you could think of these computer generated shots as a simple random sample from the population of all possible shots. Again, if we just had someone go and shoot 50 shots, that's not quite random because those are all on the same day. Maybe the shooter was sick. Maybe they had something wrong with their muscle. Who knows? So if we just had somebody shoot 50 times and they made 32, that's not random. So this analysis would not be quite as accurate. So we would just keep in mind the computer is just doing it, so it is a true random sample. So 10%, we're not sampling without replacement. So again, every shot you could think of, the computer could generate infinitely many shots. So there really is no finite population. There is no we are not sampling without replacement. So we don't have to check the 10% rule. That's only if we are doing it without replacement, which we are not. In the large counts, zero point 0.8 times 50 is 40, and 0.8, 1 minus 0.8, which is 0.2 times 50 is 10. So they're both at least 10, barely, but they're both at least 10, so this condition is met. So we meet all three requirements. Now let's carry it out. So if that null hypothesis is true, then the player's sample proportion of made free throws in a simple random sample of 50 shots would vary according to a normal curve, or approximately normal curve, with mean equal to zero point 0.8. Again, this is what we talked about in chapter 8, but that mu of p hat is equal to the actual parameter p, which is equal to zero point 0.8. And the standard deviation is p times 1 minus p over n, which we calculate to be 0.0566. All right, so we end up with something that looks like this, and p hat all the way down here. Already, just visually, it looks kind of unlikely. So we'll get back to that in just a second. So a significance test uses sample data to measure the strength of evidence against the null hypothesis. Here are the principles that apply to most tests. So the test has to compare a statistic calculated from sample data with the value of parameters stated by the null hypothesis. So again, we're looking from sample data, trying to infer from sample data what the population proportion would be. And the values of the statistic far from the null parameter value in the direction specified by the alternative hypothesis give evidence against the null hypothesis. So again, basically, this is just saying the if p was actually 0.8, getting p hat equals 0.64 is leads us to believe that the null hypothesis, we might want to reject it, right? If I had gotten 0.2 in my random sample of 50 shots, that would be even stronger evidence that I should reject the null hypothesis. So when they say this stuff right here, they're just saying, how far is it, much bigger or much smaller than the actual value. So in our random sample. And finally, a test statistic measures how far a sample statistic diverges from what we would expect if the null hypothesis were true. And basically, you can think of this is basically a z-score. Remember, the z-score value was always z equals x minus mu over sigma. Well, this follows the exact same value basically. And instead of doing a single data point, we're using a statistic. And again, the parameter is mu. So it is just a z-score. So don't let that idea of a test statistic confuse you. So it says how far the sample result is from the null parameter value and in what direction on a standardized scale. So basically, it's saying how many standard deviations away from from the null parameter value is it. And remember, what does it mean when I say null parameter value? In this case, it's the 0.8, right? That's what the claim that we're testing, whether it is 0.8 or not. All right. So in our if we plug this in, we get our z-score of negative 2.83. All right, so actually, let's cover up the solution for now. In an SRS of 50 free throws, virtual player made 32. So we're back at that again. So calculate the test statistic. So if I'm looking at the test statistic again, well, actually, I guess we already did that up here. We got our this right here is our test statistic, negative 2.83. Find the p-value using table A or technology. Show this results as an area. Show this result as an area under a standard normal curve. Okay, so if I'm looking at negative 2.83, if I'm going to use technology, what I'm going to do is I'm going to come over here. Let's go to distribution, and we want normal CDF. Now, we could have just done this differently from the beginning. We wouldn't even necessarily have to compute this test statistic this way unless the problem actually asked us to calculate what that was. But otherwise, we could just go straight from our normal CDF and plug everything in. But as it is, let's just upper is negative 2.83. I'll do it both ways. And notice I get 0.0023. So if I'm looking at that, that's telling me that if I look at my normal curve, and I'm right here at negative 2.83, or p hat, if you will. Let me do it using p hat. So 0.64. What it's doing is finding this area right here. All right, so and we found that to be 0.0023, I think. All right, so let's see what we get. Again, notice we have all this stuff here, and we get that area is our p-value. So another way we could have done it is we could have just done, go back into distribution, normal CDF. We could have said, well, lower negative 1, so still something really, really tiny. Upper, let's say 0.64. Mu is 0.8. And standard deviation was 0.0566. So we wouldn't necessarily have to calculate that test statistic except the problem asked us to. That way we could have just done this, and notice I get the same value, and it's off a little bit because we had to round to get that negative 2.83. So that's the only reason why it's not exactly the same. All right, so and this is just more again, the, basically what I wrote on the previous slide. We figured out that this area here, which is the p-value, is equal to 0.0023. And this just shows both ways. One is this is our standard normal curve, which we get when we go through and use these numbers here, and this one right here, A, is, I always forget you can't see my cursor, so A, okay, that's not supposed to happen. All right, there we go. So this is the second way I did it in my calculator. So again, like we said before, we think it's highly unlikely that the person actually makes 80% of their free throws. Four-step process we've talked about quite a bit in the past still applies. So state what hypothesis, so the null hypothesis, the alternative hypothesis, do you want, etc. What do you want to test, and at what significance level? So like what alpha are we going to use and whatnot. Define any parameters you use. So again, are we going to use the population proportion, the mean, etc. What do they represent? Plan. Choose the appropriate inference method and check conditions. Again, are we looking for the significance of a population proportion, or is it of a mean? Those types of things. We haven't talked about how to do it for a mean yet, but we want to talk about that. And check conditions. So we need to check those three things. Is it random? The 10% rule, and then the n times p and n times 1 minus p both have to be greater than or equal to 10. If the conditions are met, then perform the calculations. So you can compute the test statistic, which again is z. I mean, you can think of that as z equals x minus mu over that, where again we're taking our p hat. It's in this case it's p hat minus p over sigma. And for this particular case, but if you can remember this formula here, you've got it, right? It's the same idea. And find the p-value. Again, that's that area that's looking at if we were even less than the number that we came up with, or greater than. But in the basketball example, it was less than. All right. So when the conditions are met, the sampling distribution of p hat is approximately normal with mean. This is all stuff that we talked about in chapter 8. That's all chapter 8. The z-statistic has approximately the standard normal distribution when h naught is true. So again, that's not a null hypothesis. P-values therefore come from the standard normal distribution. Well, again, it's all stuff that we just did. All right, so the one sample z-test for a proportion. So if we have a simple random sample of size n from a large population that contains an unknown proportion p of successes. So again, we don't know what p is, but we want to test the null hypothesis that is p equals p naught to compute this statistic. So we're again, you can think of we're testing the hypothesis that p naught in this case would have been 0.8 for the basketball player, right? It makes 80% of the shots. So we're trying to test that value. So the z statistic, which is the test statistic that we were talking about before, is just, again, this is just, I keep on writing it, but it's important to recognize that that's all this is. It's x minus mu over sigma. That's the terrible sigma. And so again, p hat minus p over and this is the formula for the standard deviation. So find the p-value by calculating the probability of getting a z-statistic this large or larger in the direction specified by the alternative hypothesis. So we're basically, again, if we're hypothesizing that the parameter value is actually greater than p naught, then we would look at the area bigger than z. If we're hypothesizing that the actual parameter value is less than p naught, then we're going to look to the left. And if we're saying it's not equal to, we're going to look on both sides. All right, so now let's go back to that potato chip example that we went through in section 9.1. So we had again, uh, the producer if the producer finds convincing evidence that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load from the supplier. A supervisor selects a random sample of 500 potatoes from the truck. An inspection reveals that 47 of the potatoes have blemishes. Carry out a significance test at alpha equals zero point zero 0.05 significance level. What should the producer conclude? Okay, so again, this is on the AP test. This is kind of how you want to write out. You want to perform a test of the null hypothesis is that p is equal to 0.08, and our alternative hypothesis is that p is greater than 0.08. And again, p represents the actual proportion of potatoes in the shipment with blemishes. So alpha is equal to 0.05. All right, so let's check if the conditions are met. Random. Well, it says the supervisor selects a random sample of 500 potatoes from the truck. So if we trust that that's random, then we're good to go. If he doesn't just take them off the top or something like that. 10%. So it seems reasonable again to think if we're taking a random sample of 500 potatoes, he's probably getting more than 5,000 potatoes in a shipment, right? Um, 5,000 potatoes doesn't go to that far for if Lay's is making a million bags of chips. So um, finally, large counts. If we take 0.08 times 500 and 0.92 times 500, we need both of those to be bigger than 10. So they did the calculation down here below already. So if we look right here, we see 500 times 0.08 is 40. 500 times 0.92 is 460. So they're both bigger than 10. So we can use our normal distribution when we're looking at this. All right. So now we actually do the work. So the sample proportion p hat is 47 out of 500, so 0.094, and we want to test whether that's um, whether we should send it back or not. Like, is that if we get 9.4% of the potatoes in our sample have blemishes, is that enough for us to conclude that there's probably greater than 0.08 or 8% blemishes in the whole load? So we calculate the test statistic. So so again, we wrote all the stuff up above, but p hat, that's our sample proportion, was 0.094. P naught, that's our null hypothesis proportion, 0.08. Our standard deviation, which we use the p from our null hypothesis, and we get a z is equal to 1.15. So if we go ahead and use our calculator here, let's find out. So I could do again distribution, normal CDF. If we're using a z value, remember that's we already converted to standard normal, so mu would be 0 and standard deviation sigma would be 1. So we could do we want to be greater than, so we're going to do lower is 1.15, upper is going to be 1e99, mu is equal to 0, sigma equal to 1, and we get 0.125. So I compare that value. That's our p-value, right? That's our p-value, and I compare that to alpha. Remember, alpha was 0.05. So if that's less than alpha, we would reject the shipment. If that's greater than alpha, then we're going to accept the shipment. So because it is greater than, we fail to reject. Again, I probably even in this example, I use the word accept the shipment, but we don't necessarily accept the null hypothesis. We fail to reject um, the hypothesis. So, um, but my use of accept in this case was okay. We accept the shipment, but we don't necessarily accept the claim that there's 8% of blemished potatoes. What we do, but we did not find enough evidence to say that there's not 8% blemished potatoes. So one thing that's kind of nifty, and you're allowed to do this on the AP test. You'll notice there's this little note on the side here. Um, but you can use your calculator to do all of this. So I could have just gone in here and gone into stat, tests, and it's a one prop z test. And our well, let me do our basketball example here, actually, because I think they run through and do it for the potato example. In our basketball example, um, the null hypothesis was that he makes 80%, so P naught was zero point 0.8. In our sample of size 50, so n equals 50, he made 32 shots, so x equals 32, and we want to know the probability or we think that the he's probably makes less than 80% of his shots, so I'm going to say less than P naught. I go to calculate, and notice everything that it says there. Let me go back up to our example here. We saw that the p-value was 0.0023. And if we look at our calculator here, notice p-value 0.0023. And that's a kind of basically sums up everything that we're doing in here as far as the calculation. But just be aware that you still have to follow that four-step process. You got to state everything, and you got to test. Make sure that test the three rules are met and all that good stuff. So if we do this potato one real quick, let's just try that. Let's go clear stat again over to tests one prop z test. So in this case, our p naught was 0.08, and we had 47 in a sample of 500, and we want to check the claim that it's greater than 0.08. We calculate. Notice we get our p-value of 0.124, and that's basically what we got. Again, it's off by a little bit of rounding here, but that's just because like that 1.15 is not an exact answer and everything like that. So kind of nifty. Nice quick way of doing it on our calculator. Two-sided tests. This is just not necessarily that we think it's lower or higher, but just that we think it's not accurate. So basically, it's in either direction of the observed value of p hat. So basically, what this ends up being is we have to look at both tails on the right and the left. So let's just do an example real quick. According to the CDC website, 50% of high school students have never smoked a cigarette. Taeyeon wonders whether this national result holds true in his large urban high school. For his AP Stats class project, he surveys an SRS of 150 students from his school. He gets responses from all 150 students, and 90 say that they have never smoked a cigarette. What should he conclude? Give appropriate evidence to support your answer. So again, let's state the problem. We want to perform a significance test using the hypotheses. The null hypothesis is that p is equal to 0.5, and our alternative hypothesis is that it's not equal to 0.5. All right, so because, and one thing, notice no significance level was stated, so you can, if there isn't one, pick one that's reasonable. You don't want to use like alpha equals 0.5 or something like that, but kind of think about our confidence intervals, which we'll tie in again pretty soon. We would use 90% confident or 95% confident or things like that. So pick something reasonable, like you probably wouldn't want anything really alpha bigger than 0.1 in most cases. It depends on the scenario, but generally speaking, it's using alpha equals 0.05 is a good way to go. So let's check if the conditions are met. So random says SRS 150 students. Done. 10% rule. Can we guess if it's does it say it's a large high school? No, it just says a high school. Or yeah, large urban high school. There you go. So if it's a large high school, you can assume there's probably more than 1,500 students in there. So that's very, very reasonable. And finally, we need to check p is equal to 0.5, where again, this is this. A lot of times we don't label that as p naught, but that's what that is. So we check, does 0.5 times 150 and 1 minus 0.5, which is still 0.5 times 150. So 50% of 150 is 75, which is greater than 10. So it probably says that on the next page. So I get 75 in both cases, which are both at least 10. So we can do our normal calculations. So I'll show you how to do it on our calculator again one more time. But we calculate our test statistic. So we plug in our p hat was 0.6 because 90 out of 150 So this 0.6 came from 90 out of 150 minus P naught, which is 0.5, and then again using the standard deviation using our P naught as well. So we get our z-score of 2.45. Now, if I look at that, I could, again, we can go the long way, just make, because I think this is valuable to make sure we understand what's going on here. We don't want to just know how to do it on our calculator and have no clue what's going on. So I want to know 2.45. I want to know the likelihood that it's above that. Now keep in mind, so 0.007, this right here is 0.007. All right. Now, uh, we're not figuring out whether the alternative claim is not that it's higher than 50%. It's just that it's not 50%. So we end up having to use both tails. So we also need to calculate that area. Now the normal curve is symmetrical. So what that means is basically we get to take 2 times that value, and that's where they get this 0.0142. They must not have rounded quite as far as I did. You can see 0.0071. But basically that's why we double it, because we got 2 of them there. And so we get 0.0142. That p-value is less than the than alpha, and so we would reject the null hypothesis. We do not believe that the proportion of students that smoke in high school is 50%. So one more time on the calculator, if we go to stat tests 5, which is one prop z test, p naught, it was 0.5 in this case, x was 90 people, students that didn't smoke out of a sample of 150, and we want to know that it's not equal, and so we do calculate. Notice there we get our p hat, or sorry, p, not p hat, p value of 0.0143, again less than 0.05, so we reject the null hypothesis. So sometimes confidence intervals will give us a little bit more information. So if we went through and calculated a 95% confidence interval for what the true population was, again, this is back from chapter 8, based on that random sample where 90 said they hadn't, what we would do is, again, is use our good old formula here. Z star is our critical value, standard deviation. And so we calculate that for 95% confidence interval, the critical value is 1.96. And remember, if you just look at that comes from our normal distribution. Where does how many standard deviations have exactly 95% confidence? And that's, we always rounded to 2 before, but starting in chapter 8 we didn't, and so we had to use 1.96. And so we do that and we figure out that's between 52.2% and 67.8%. We're 95% confident that the true parameter value is between 52.2 and 67.8%. So if you think about that, there's actually a direct relationship between whether this interval here contains the null hypothesis value. Like in this case, if this had contained 0.5, it doesn't, but if it had, then we would have failed to reject our hypothesis. And that's because alpha equals 0.05 has a direct relation to 95% confidence. Again, if I said alpha is equal to 0.1, that would be exactly the same as checking whether it lies within the 90% confidence interval. So that's kind of interesting. They're really closely related. So, and that's basically what I just said right there. All right, now for the one actual truly new concept in this section is about the power of a test. Now, some of the stuff in this slide, let's actually go through and do an example, because I think the example makes it a little bit clearer than some of this language is hard to follow. So, but the short definition: the power of a test against a specific alternative is the probability that the test will reject the null hypothesis at a chosen significance level when the specified alternative value for the parameter is true. So what that means basically is, let's do it in the context of the potato chip problem. So the potato chip producer wonders whether the significance test with the null hypothesis that p equals 0.08 versus the alternative hypothesis that p is greater than 0.08, based on a random sample of 500 potatoes, has enough power to detect a shipment with, say, 11% blemished potatoes. In this case, a particular type 2 error is to fail to reject the null hypothesis when p equals 0.11. So basically what we're saying is, uh, what how likely is it, based on our sample, that we might get a type 2 error? So what is a type 2 error? Again, remember it's fail to means type 2. So if we fail to reject the hypothesis when we should have, when we were incorrect. For instance, in the last case, we didn't reject the shipment of potatoes because it didn't meet the significance level. Um, but suppose we didn't reject it, but it actually ended up having um, more than 8%, or in this case, say 11% blemished potatoes. So we went through and found the probability or of a type 1 error, and we got um, basically that the p hat value was 0.0999, um, and so again, we use alpha equals 0.05. So basically, if we ended up with anything bigger than that p hat value for our sample, um, then we would reject the shipment. So what we're going to look at is how many times, what's the likelihood that if the true parameter value was 11%, like suppose the shipment actually had that. So if our true parameter value is 11%, what is the probability that we basically accept it anyways? Um, So in this particular case, the type 2 error is to fail to reject the null hypothesis p equals 0.08 when p actually is equal to 0.11. So suppose, again, all this stuff is that we're doing is we don't know what the true population is, right? We're the hypothesis, the null hypothesis is that p equals 0.08, but we don't know whether the population is equal to 0.08. That's what we're trying to test for, right? Well, what if we don't, we afterwards we go through and test every potato and we found out that a shipment had 11%. Um, and it's like, what is the likelihood that we would have accepted um, that shipment? That's what we're trying to figure out. All right, so if we look at it and we do, actually, let's just do the calculation on our calculator just to see kind of where this comes from. But basically, if you look at this is our um, sampling distribution of p hat if the true parameter value was 0.11. So if we do that, notice if I do the calculation here, if I do normal CDF of 0, from 0.0999 up above, but you do it where mu is equal to 0.11 instead of 0.08. And if I go ahead and do this calculation, I'm just off by a little rounding, I think, but I end up with this number here being the area under that normal curve. So what ends up happening is, in that case, this area represents the number of shipments that I would reject using my calculation that we did above. Um, but if the true population was 0.11, that means about 75% of the time we would reject it. But this is right here is 0.25 ish. So 25% of the time, even if there's 11% blemished potatoes, we would still accept it, accept the shipment. So fail to reject the hypothesis. We would still accept the shipment about 25% of the time. And that's what the power is talking about. So the quick, easy way to think about this is if if we just find the probability of making a type 2 error, which well, in this case, we'll call it beta, then we could look at the power of a test against any alternative is 1 minus beta. All right, so again, when we're testing the power, we'd have to test it against 10% or 12% or something like that. But there might, for instance, be the idea that, well, we absolutely don't want to accept anything with 15% or more. And so you could go through and figure out the power. You want that power to be um, less than a certain number or something like that. So, but that's where power comes into play. So, and to be honest, I'm not sure why this graph has a little bit different, but notice the number here matches a lot closer to what I have there. And so basically we've covered everything that we want to. Power is the only thing that's new, but remember we're just testing the power against an alternative hypothesis. So um, again, just looking at how likely we are to make it, fail to reject when we should have rejected.